Okay, so today we're going to continue where we left off before the break. So here's our setting. We're going to have a system, a linear state space system. And we'll call this we're going to call this WT plus 1. And WT plus 1 is going to be an IID, normal 0 I sequence. And this is going to be true for t greater than or equal to 0. And we're going to start the system off with x0 being distributed normally with, we're going to call it mean x0 hat. We'll see why we call it that in a minute. And covariance matrix of x0 around x0 hat of sigma 0. So xt is Markov. And the conditional distribution, another way to write this is the conditional distribution of xt is normal for t greater than or equal to 1. Okay, but now we're not going to, this is going to be a hidden Markov model. Or so-called HMM. And what we're going to observe at time t is a linear combination of the state plus a random variable Vt. You could call it measurement error if you want. You could think of it more physically. And Vt is going to be normal 0 mean R. And we're going to assume that Vt and W t plus j for all t and j. We're going to assume that they're orthogonal. So given the Gaussian, that's equivalent with their being independent. So this can be modified. We can make them dependent and allow them to have, and there's a reason I'm not modifying it here, which you'll see later, maybe. Okay, so this specification actually implies that y0 is going to be normal. Well, it's going to have, we can get out it's normal like that, and we can so what we want analogous expressions for other t's greater than or equal to greater than 0. That's one thing that we're going to want. And we're going to want to interpret this. This might seem a little vague right now, but hopefully it'll become clarified. So now I have to, tell you we're going to have a decision maker. Think of it as us. And what he observes, the decision maker is going to observe, well, he's going to observe yt for t equals 0, 1, and on up to t. he observes this. And that's all he observes. He knows the structure, which means he knows A, C, x0 hat, sigma 0, G, and R. He knows all those things. And those things are the parameters of the state space system and the measurement error equation. So this is the state evolution. And this is the observer equation. So one thing you could ask is, what do you mean state? What do you mean? So xt is the state for the Markov process, the hidden Markov xt process. But one thing you might ask vaguely is, well, what's the state for yt? Because at the end of the last lecture, I indicated that in general, yt is not Markov. So we have like finding the state is an art. Okay, so one way that we could reason is just loosely, well, maybe loosely or not, is if I wrote down the joint density of a history x0, I can factor that like this because of the Markov process assumption. I'm back. Where I'm using F as the generic notation for a density. If I try to do the same thing for yt, well, I can do this. I can do this all right. But now if I ask myself, what is the state for yt? Well, it's not Markov. It's the entire history. And I could write this, and I could write this yt minus 1 with, that's the understanding that is the partial history from t to t minus 1. That's a game theorist who would write it that way. The quote-unquote state is, for the conditional distribution, is at time t, it's this entire history. It's not yt minus 1. That's just true in general. I'm asserting that. Later on, I'll give you some machinery, or in the chapter, there's machinery for convincing yourself of that, for proving it. Okay. So now here's what we might want. Is there a low-dimensional state that summarizes y0t minus 1 insofar as it determines the conditional density is there some low-dimensional state that summarizes it? That's a question mark. So do we really have to keep track of all the history like that, or can we? Is there something that maps this history into something of lower dimension? And the answer is going to be yes. And what it's going to be two numbers that I'm going to call x hat t and sigma t. It's going to be that. And what those are going to be is, these are going to be literally sufficient, it's legitimate to call them sufficient statistics for the conditional distribution of y t at t. And these statistics, I haven't told you what they are, will verify the formula yt is distributed normal. Now maybe you have seen this before. G oops, dyslexia. G x hat t, G sigma t G prime plus R for t greater than or equal to. Now it's going to be t greater than or equal to 0. So this is all wish. This is all want. And then this is want, and this is a promise. Promise from me. Okay, and what we notice is that this formula, that's identical with this formula at time, it's the extension of that formula to all t's. And we got, okay, so how do we get that? And then for this to be useful, is we need evolution equations to use this for x hat t and sigma t. So we need that. Okay, so these are going to be supplied by the celebrated, all this is going to turn out to be correct. Evolution equations of this are going to be given by the celebrated Kalman filter. And I believe that this was actually Rudolf Kalman's PhD thesis at MIT, where by using basically one insight and looking for having the instinct that there was some state variable lurking, that he could make something recursive that people didn't realize, very smart people didn't realize was recursive before. That's one thing he'd want to do. He wanted things to be recursive. And then his tool was that you can regress anything on anything else. That's his idea. He knew that. So that's what we're going to do. We're going to follow him. So background, we're just going to use one tool, which is going to be linear least squares regression or projection. And the idea is we're going to have two vectors, y and x. These are big Y and X. They're not connected to what we talked about earlier. They're just two arbitrary random vectors, and they have some joint distribution f, and then we're going to assume that the mean and the covariances are all defined. And then what we're going to do is we're going to get a projection. We're going to represent y is equal to beta x plus epsilon, where epsilon is orthogonal to x. That identifies beta x is said to be the linear projection or linear least squares projection of y onto x. And we have a formula for this. It's the population least squares formula. It's in the chapter. It's all over the place. Where everything inside is a matrix and things are defined, so this is conformable. So that's the least squares. That's the inverse of the second moment matrix of the x's, and it's pre-multiplied by the cross moment matrix between the y and x. So that's a least squares formula. So what Kalman is going to do, he's going to notice the following thing. Given a c x0 hat, sigma 0, g, and r, he can compute any cross moment in sight. He can do that. He has all the information to do that. That's one insight. And the second thing is his strategy is going to be regress what I don't observe. So what is that going to be? Well, he's never going to observe xt. But I don't observe xt on what I observe. And what's he going to do it? What he's going to do it, he's going to do that is what I observe, and that's going to be at t minus 1. So he's going to regress that on y t minus 1, y t minus 2, all the way back, y0. That's the second idea. And the third idea is he's going to simplify the regression of formulas by now here using a Gram-Schmidt process that instead regresses on an orthogonal basis at minus 1, a0 for yt minus 1. y0. That's the idea. So you can compute any moment. The strategy wants to regress what he doesn't observe, what he observes, what he doesn't observe, on what he observes from the moment matrices. And then he's going to simplify things by reformulating this information into an orthogonal basis. And what an orthogonal basis means that at minus 1 is orthogonal to as for all t minus 1 not equal to s. And if you look up Graham Schmidt on Wikipedia, there's a procedure for doing that. And that procedure can be interpreted as running some regressions sequentially. And that's exactly what following in Kalman's footsteps we're going to do. So let's begin the exciting process of following Kalman's footsteps. And just a little digression. Two of the most important useful and important ideas for economists and other people that study dynamics that emerged in the mid to late 20th century are the Bellman equation, the formulation of dynamic programming by Bellman, and then the development of the Kalman filter. And both preceded by recognizing that a problem could be vastly simplified if a recursive structure underneath could be identified or imposed. And there's an intimate connection between what Kalman did and what Bellman did, even though superficially the problems look very different at the beginning. Okay, so let's follow the footsteps of Kalman. So we're gonna move through time. Now there's something. So what did Bellman do? What Kalman's going to do is he's going to go forward in time. He's not going to work. He's not going to work backwards. He's going to do just the opposite. He's carefully going to go forward in time. What Bellman did is he worked backwards. He works backward induction. Now Kalman's going to go forward. So here's the deal. Let's just do. I'm going to write this like this. He's going to come into the period, and I'm going to write this t is equal to -1. So what does he know? Well, he has this belief about, he thinks x0, which he doesn't know, is going to be distributed normal. I'm just going to write down everything he knows before he comes in. And what does he think? He thinks this is x0 hat and sigma 0. These are parameters of the problem. And they characterize, what a Bayesian like Cogley would say is, this is what the person believes. So this would serve as his prior. And then it follows immediately, since he believes that model, that he believes that y0, which he has not seen yet because it's time t-1, is distributed g x0 hat, and it has covariance matrix given by our formula. This is what he thinks. Okay, and then time t equals 0 happens. Time t equals 0 happens. Okay, so now what happens is y0 is observed. Okay, and now what we do is we form what we could call a surprise, or we'll call it an innovation. And what that is we're going to call it A0, and it's the difference between Y0 minus the mean. It's the deviation of Y0 from what we thought it would be. Now, at time, if we calculate as of time t-1, the conditional expectation of A0 is 0. On average, that's by construction. If we just take the conditional expectation of y0, it's equal to gx0 hat. So this is that's a surprise. If it's anything other than 0, we say that it's a surprise, and we call it an innovation. Okay, so now the person knows the innovation. So what does he do? He's going to regress what he doesn't know on what he knows. So he's going to regress. He's going to regress x0, which he doesn't know, on a0. Or we could say he was going to regress it on y0. Now it's going to turn out a0 is going to be the start of an orthogonal basis for yt y0. Maybe the start. So you'd get exactly the same answer in terms of projection if you regressed on either a0 or y0. But well, I'm going to just regress on y0. So now we just have to use our formula. So he's going to run this regression. He's going to, here's what he wants. I write this down. He knows x0 hat, so I'm going to write it down this way. And I'm going to call L0, that's my regression coefficients. And this is what I'm regressing on. This is my A0. And this is a random error. And we're going to impose that epsilon is orthogonal to A0. It's my least squares. Orthogonal projection. My least squares orthogonality condition. And some people like Sims and Hansen and Schiller got very famous by, in different contexts, exploiting this orthogonality condition. Okay, so if we just, the least squares formulas, if we just apply the formula that we had, it's going to be this. We just do our work. These are my moment formulas. I'm just writing this out. Be pedantic. So it's going to turn out then that my least squares formula for L0, Lars Hansen just calls this running the regression. Many papers that he writes use this. Okay. So now what he has is, I'm going to call this, I'm going to call the following object. I can call E of Y, I'm sorry, E of X0 after having seen Y0. That's what I originally thought, plus L0 times Y0 minus GX0 hat. So L0 tells me this is the regression coefficient of X0 minus X0 hat on the innovation, on the surprise. Okay. So now what I can do, okay, let's just pause there for a second and stare at it. So this is all, I'm doing all of this at time 0. After I've seen X0, after I've seen Y0. Okay, now we're just going to scratch our head for a minute, and we're going to say, well, what do we know? What about X1? Well, so we know that X1 is equal to A X0 plus C W1. We know that. So what that means is that we just do a little algebra, And we can calculate that E of x1 given y0, next period is like given y0 or given a0, is going to be equal to a x0 hat plus I'm going to write this way, plus L y0 minus g x0 hat. So all this is this is going to go to 0 because I don't know what it is, the expectation. And I'm just replacing this. I'm replacing x0 here with E of x0 condition on y0. That's all I'm doing. If I do that substitution, I get this equation, which I can write as this way. E of x1 condition to y0 is equal to a x0 hat plus, I'm going to call this k, oops, this was L0, k0 y0 minus g x0 hat, where k0 is given by this formula. It's just equal to a times L0, but I'm going to write it out. So this is an important equation. And I'm going to define this thing. I'm going to define E of x1 given y0 as x1 hat. I'm just going to define that. And more generally, I'm going to define E of xt given yt minus 1 back to y0, which is the same because it's going to be the same as xt given at minus 1 on back. I'm going to define that as x hat t. And the key thing is, this is the expectation of xt conditioned on the information that I have up to the previous period. This was a shrewd choice that Kalman made. Okay, so now look what I have. I just have to do one more thing. I'm gonna note that I can just use the formulas that I already have and write this down. And I'm going to substitute in y0. And all this is just y0 here. You just substitute in. So that's what x1 minus x1 hat means. And now what I'm going to do is I'm going to compute, and I'm going to allow you to do this in private. I'm going to compute this. And that thing is nothing more than, I'm going to call that sigma 1. Sigma 1 is the covariance matrix of x1 around my estimate of x1 based on having seen y0. And if I just take the transpose of the right-hand side, multiply it through and take expectations, I get this formula. Get this formula. This is a formula that maps sigma 0 and things that I compute at time 0 into a sigma 1. And so now what I know is I know that the conditional density of x1, condition on y0, is going to be normal x1 hat, given by that formula, and sigma 1. And now I'm just going to collect equations and stare. Okay? Oops. I'm just going to collect equations and stare on what we have above. As I've done my job, I've extracted all the information that I have. So I'm going to write the equations in a particular order. The first thing I did is at time t equals 0. What do? I form these equations sequentially. The first thing I do is I compute this. Second thing I do, by the way, I could do these two things simultaneously. You'll see what I'm saying, why I say that. I actually could have done this thing first. Copy these formulas. By the way, K is sometimes called the Kalman gain. Kalman gain. Okay, so at t, I form these things. So at t, so I started out. So what's the deal? At t, I start knowing. What do I start knowing? I start knowing x0 hat sigma 0. And then I observe y0. Let's see if I can do everything. So then what I do is I do things in this, I form A0. Actually, you know, what you'll notice is I could have done this right away. And after I've done this, I could do this. I could have done this right away. But to do this, I have to know K0. Okay. So what I come out of here is I leave knowing that the conditional distribution of x1 is normal x1 hat sigma 1. I leave knowing that. And I also leave knowing that the conditional distribution of y1 is normal g x1 hat g sigma 1 g prime plus r. I know that. But now if you stare at this, I'm now, Kalman has completely recursified things, because this looks just like the situation that I started with, except instead of x0 hat sigma 0, it's x1 hat sigma 1. So you just do it again. So what I can now do is, if I just do this again, each period, I end up with these recursions. Yt minus g xt hat, kt equals a sigma t, g prime, g sigma t, g prime plus r inverse, x hat t plus 1, I now update this, a x hat t plus kt times at, and then sigma t plus 1 is equal to c prime plus kt r kt prime plus a minus kt g sigma t a minus kt g prime. And this, starting from x0 at sigma 0, I need my initial conditions. This is the celebrated Kalman filter. And what we have achieved is we have gotten some sufficient statistics x hat t sigma t for the conditional distribution f of yt plus 1 conditioned on so it turns out that the sufficient statistics for this are going to be, and we've got a recursive algorithm that maps the recursive algorithm maps x hat t sigma t, and then it maps yt into x hat t plus 1 sigma t plus 1. That's the Kalman filter. Just a remark, just by doing a little algebra and rearrangement, the formula for sigma t plus 1 can be rewritten like this. It's just an equivalent form. We can eliminate, essentially what I'm doing is I'm eliminating kt by substituting in the formula for kt. So this is another formula people use. This is an equation that maps it maps sigma t, it maps A, C, and R into a sigma t plus 1. Is their equation. And it has a name. It's called a matrix Riccati difference equation. And then I'll copy down another formula. I want to do something here. Just copy this formula again for the Kalman game. So this pair of equations, star and star star. And so you remember when Yarda talked a little bit about dynamic programming, and he did backward induction, showed you the Bellman equation, and then you wrote down a strategy for solving the Bellman equation, which was to iterate on it. And then for infinite horizon problems, you asked whether those iterations converged. And it's like for the infinite horizon problems are often easier than finite horizon problems because decision rules end up not depending on time. They're time invariant decision rules. So what's the counterpart here? One might want to know is under what conditions we don't work backwards. Under what conditions does sigma t converge to something? Because if sigma t converges, then kt will converge. And it looks like you have a chance for it to converge because we've set this up so that A, C, and R are independent of time. So it turns out there are conditions for this. They're not Blackwell's conditions. So, so oftentimes these conditions are satisfied, and what they amount to saying is if this system operates for a very, very long time and we have a very long history, then the Kalman filter, the sigma t and the kt converge to just constant numbers. And this is called the time invariant Kalman filter. Okay, so I'm almost ready to stop. So what I want to tell you is that the Kalman filter has been a remarkably useful tool for solving a bunch of problems that at first sight seemed intractable. It's used extensively in theory and econometrics, and it's used today in some quite modern papers about higher order beliefs. It's used to understand what the relationship between vector autoregressions and a theory is. And we might talk a little bit more about that, but this is a very powerful tool. And I'm going to ask you to sort of, these two formulas, star and star star, I want you to stare at them. So an example would be one example, and it's in the textbook, it's an example where we apply the Kalman filter to a well-known problem of John Muth. It's actually Yu's first paper on rational expectations, where he cracked a very hard problem, but very few people could read Mu's paper, which was written in 1960. Very few people could read it. He did not use the Kalman filter, which was actually, I think, first published in 1960. He used a different method. And his paper is a 30-page paper with lots of complex analysis and pretty remarkable paper. I think I'll tell you about it in class. With the Kalman filter, you can do it in just a few lines. You do that magnificent 30-page paper in that by using this machinery. Boyan Jovanovic has written a number of remarkable papers where the Kalman filter is at the core. It's a good tool to know, no matter what field of economics you want to go into.